Hi everyone, I'm Arvind Neelakantan. I'm going to talk about efficient non-parametric estimation of multiple embeddings per word in vector space. This is work I did with Jeevan, Shankar, Passos, and Andrew McCallum at UMass Amherst. So vector space embeddings are now increasingly popular in NLP, and here words are represented using real valued dense low dimensional vectors, and they're very useful in the sense because these vectors are learned using large amounts of unlabeled data, and when you plug in these as features in supervised models, they usually help you to generalize better. And these vectors usually arrange in nice clusters of related words. So I've shown here a cluster of fruits and cluster of company names. And but a problem with most of previous work in vector space embeddings is that they learn a single vector for every word type, ignoring polysemy. So if you have an ambiguous word like apple, a situation like this happens where it is close to cluster of fruits and cluster of companies. And this reduces the effectiveness of using these vector embeddings in downstream tasks. A second, more subtle but serious drawback, I think, happens because of triangle inequality. So the word apple is close to cluster of fruits and also cluster of companies. And because of triangle inequality, cluster of fruits and cluster of companies are pulled closer to each other. And this would be like really confusing if you use it in a supervised model. And so this is the motivation for learning multiple embeddings per word. In previous work for this task, a common theme is to cluster every word type independently. So you cluster tokens for a word type into, say, K clusters, and you relabel the corpus with its cluster membership, which is the sense for a word token. And once you do this, you run your usual embedding learning algorithm. So there's been two particular works which is very close to our work. One learns multiple sparse high-dimensional vectors, and the second one learns multiple low-dimensional embeddings. And they do not scale to large vocabulary sizes. And I think a part of the reason is that you need to run this clustering algorithm for every word type in your corpus independently. So a corpus has a lot of word types, and if you need to run your clustering algorithm, say 30,000 times, it's going to be very slow. Our goals is to develop a joint model for word sense discrimination and embedding learning so that it's more scalable. And we also hope that this is going to be more accurate because the embeddings could help you to identify word sense better, and vice versa too. Because if you identify word sense more accurately, hopefully the embedding quality is also better. And the final goal is to learn a non-parametric model, so where I capture varying number of senses per word. And in a lot of previous work, they assume that every word has K senses, which is not true. And this is also different from previous work that was discussed here, the first talk, where we do not assume we have a sense inventory or things like that. So it's completely unsupervised. I'm going to start describing the skipgram model, which is useful background for our work. So here for every word token, you collect a set of context words. So here I've picked 2 words to the left and 2 words to the right of the word apple. So the sentence could be something like, computer manufacturer Apple was sued, so on. Okay. And in the skipgram model, the probability that a word C is observed in the context of word WT is given by sigmoid of dot product between the vector representation of the 2 words. So, for example, to get the probability that manufacturer is a context word of word apple, you take the sigmoid of dot product between the vectors of those 2 words. And for training, for every word type WT, you collect a set of context words, and you want the probability of assuming this seeing this pair to be high. And you also get a contrastive term where you get a set of noisy context words. These are words that are not observed with the word WT. And you want the probability of seeing this pair to be low. So you can think of this whole model as the word vector of Apple is trying to predict the context vectors. Okay. So now I'm going to talk about our first model, the multi-sense skipgram model. Here, each word has k senses. K is a hyperparameter, and a word has a global vector representation, which we use when the word occurs in the context. So V subscript G is the global vector representation of the word. And a sense is represented by a pair, which is basically a context cluster and a word sense vector. Okay, and the first step in the model is to predict the sense of a word token when you're given the context. And here the high-level intuition is that if you have words like computer and manufacturer, then the sense of the word apple is probably Apple the company and not the fruit apple. Okay, and how we do this is we first get the vector representation of a context, which is average of the global vector representations of the words in the context. And then we pick the cluster that has maximum similarity with this context vector. Okay, this is very simple and sort of related to previous work, but the crucial difference is we do this when we are actually learning the embeddings and not as a pre-processing step. Okay, and once we predict the sense of a token, using that picked sense vector, we predict words in the context. So this step is similar to the skipgram model, and the difference is that instead of using just a single vector for the word, we first pick the sense vector, and then using that sense vector, we try to predict words in the context. And one detail I forgot to tell you is that when I pick the sense of a token, I add that context vector to the cluster. So the cluster center keeps getting updated. So this is the MSSG model. And the training objective is same as the skipgram model. So this is good. We've got a model which learns multiple embeddings, but it is not non-parametric. So the next is the non-parametric MSSG model. So the basic setup is again the same. You have a global vector. You have a global vector for a word, and sense is represented by a pair, a context cluster, and a word sense vector. And the difference is when we try to predict the sense of a word token, we first pick the cluster that has maximum similarity with the context. Okay, and if the value is greater than lambda, we go ahead and use that sense. And if it is not, we create a new sense, which is basically having a new context cluster and also a new sense vector. Okay, and here lambda is the hyperparameter, and it is the only hyperparameter in the model. So we use lambda to control the number of senses the word has. And once we pick the sense, it's again similar to MSSG model, where using the predicted sense, we use that sense vector to predict words in the context. Okay, so these are the two models. Now some experiments. We use the Wikipedia corpus, which has close to 1 billion tokens. And we use same setting as previous work, where multiple embeddings were learned for a 6,000 subset of the 30,000 vocabulary. I think this was like picked basically to have words that have many senses. And just to check how good our method is with like all the words in the vocabulary, we also run experiments where we learn multiple embeddings for all the 30,000 words. Okay, and for the MSSG model, we use the number of senses as 3. First, some running time results. So the baseline model takes a week to learn multiple embeddings for 6,000 words. And you can see our model, the running time is comparable to ScriptRam. So even though we learn multiple embeddings, it's probably 4 times longer, but we can train multiple embeddings in like 6 hours on 1 billion tokens. So this is the number of word senses that are learned by the non-parametric model. And you can see it's reasonable because a lot of words have 1 or 2 senses, and very few words have like 9 senses or 10 senses. Now some nearest neighbor results. What I've done here is I've shown the nearest neighbor for each sense vector. So the MSSG model always has 3 senses. And in these 2 examples, I've picked basically words that the non-parametric model gets 1 sense or 2 senses. And you can see for Apple, sort of gets the first row is for fruits and the second is for companies. And for the skipgram, it's confused between company and the fruit. And this is for a word which the non-parametric model gives 3 senses. The first is mercury as the chemical element, and second is Mercury the planet. And the third is, so there's a company called Mercury Records. It's a music production company that markets music recordings and videos. And all the words in the third sense are record label companies, like OK, Deram, Network, are all record label companies. So the model gets 3 senses, and the nearest neighbors look quite clean here. Now some quantitative experiments. So the first task we evaluated on is called WordSim 353. Here you're given a pair of words, and you need the model has to give a score saying how similar they are. Okay, and then humans also give a similarity score for all the word pairs, and then you measure the correlation with your predictions with the human judgment using Spearman's correlation. So for getting the similarity score, we use 2 different similarity measures. One is the global sim, where we measure the similarity using the global vectors. And average sim uses the sense vectors. So you average over the set of all sense vectors. Okay, and these are results on the WS353 task. So we perform better than the baseline that learns multiple low-dimensional embeddings, and we also perform comparable to skipgram, but the sparse high-dimensional vectors perform better than our model in this task. Okay, so the second experiment is probably a better way to evaluate this setting, where along with the word pairs, you're given the context in which they appear. So in the first example, the task is basically to give the similarity between the words bank and money, and you're also given the context in which they appear. So this is sort of a more, actually, I think it's a better way to evaluate these multiple embeddings. So here, apart from the 2 metrics, global sim and average sim, we have 2 other measures, since we have context along with the word pairs. The first is average similarity in context, where you measure, you get the similarity scores between each of the sense vectors, and you weight it with how compatible that sense is given the context. Okay, and the 4th metric is local sim, which is very strict, I think. So here, given the context, you need to predict the sense for that token, and you're allowed to use only that sense vector. So this sort of measures also the ability of the model to perform word sense discrimination, since you have to pick just one sense vector. So here are results on word similarity in context task. We perform better than both the baselines here, the one that learns multiple high-dimensional vectors and multiple low-dimensional embeddings. And I think the really impressive result was with the local sim metric, where we perform so much better than the baseline method. And this sort of shows that the vectors are good enough to do even word sense discrimination, because you need to pick just one vector given the context, and we perform twice as well as the baseline method. And so this is to measure the effect of embedding dimension on for the MSSG model. And so once we get to 300 dimensions, the performance is very stable. And this is to measure the effect of number of senses. So the baseline method that learns multiple low-dimensional embeddings, the hyperparameter was 10. So they estimate 10 vectors for every word. And I think that that gave the best results for them. And even when we use 10 sensors, we beat the baseline model in all metrics. And again, with local sim, we perform twice as well as the baseline method. I think with 10 sensors, it's really hard to get the local sim right because the probability of picking a wrong sense is much more when you have 10 sensors. So if you remember, all these experiments were when we learned multiple embeddings only for the 6,000 words that was used in the previous work. So we ran experiments where we learned multiple embeddings for all the 30,000 words. And this is WS353, where you're just given the word pair and not context. And this is word similarity in context. And you can see that the numbers don't drop a lot, which sort of shows that our method is robust to noise. And the numbers don't go up because the words in the test set were all there in the 6,000 subset itself. So that's why the numbers don't go up. And it's good that the performance don't drop as we add more words in the vocabulary set. So to conclude, we focused on this task of learning multiple embeddings per word. We proposed a joint model for word sense discrimination and embedding learning. And we also have a non-parametric version that captures varying number of senses per word. We got state-of-the-art results in word similarity in context. And the method is fast and robust. And finally, the code and word vectors are available in my web page. Thank you.
You have time for lots of questions.
I have two questions. So first of all, so you're learning multiple embeddings for the words, but not for the context words. So
yeah, we use the global. So I think I should have explained that. So why we do that is basically, if you do not have global vectors, then we need to do this joint optimization to pick the sense for the current word and words in the context, which is going to increase your training time. And that's the reason why we have global vectors.
Do you think it would help though?
We are actually trying. We're running experiments right now. So this word similarity task, I don't know whether it's going to matter. Like that's the results. So, but we are now planning to run experiments on word sense discrimination, NER, like learning representations for paragraphs. And I think in those settings, it's going to be more useful.
Yeah.
And there, I think we'll see whether picking these senses jointly, even though the training time is going to go up, I think the quality of word sense discrimination is going to be better.
Yeah. And then my other question was for the word similarity task, did you try maximum similarity rather than average? Because it seems like if you ask people without context, it's similarity between two words, they're probably thinking about the max.
So we did try maximum similarity, but it was like very similar to the thing. Yeah. Thanks.
So in 2002, Sam Royce and Jeff Hinton has a paper on called stochastic neighbor embedding. In that paper, I think they did similar things like they think one word have multiple embedding.
Is it the paper in calling this year?
No, it's in 2002's NIPS.
2002?
Yeah, NIPS. It's the author's name is Sam Royce and Jeff Hinton. Okay. They called their model stochastic neighbor embedding. In that paper, they exactly gave the example of the word bank, and each word they assume they have multiple embeddings, and they use mixture models to mixture their meanings. So
this is very similar to sorry.
Yeah, I think that's why I asked you this question. Do you have comments of the difference of that work?
Okay, so I think so first thing is it's sort of built on top of the skipgram model, which is new, and this is actually a mixture model. So when we train, instead of doing like soft clustering, we are doing hard clustering where we pick a sense. I think in mixture model, if you train in a mixture model setting, you would sort of do soft assignments where you'll have probability of this sense. And when we tried training with that metric, with that objective function, the performance did not improve much with using the stochastic version. And I don't know whether they do it when they actually learn the embeddings, or is it done as a pre-processing step, which I'm not sure. Yeah, thanks.
Thanks very much for a good talk. Can you speak a little bit about how you choose the parameter of lambda for the threshold?
Sure. So we basically do this. We did not play around much with that because we really do not have a task to measure the number of sensors. So we just, on the validation set, so we have a validation set which is like 1/10 of the training data or something. And if we get something like this, where it's reasonable number of sensors for a word, where like a lot of words don't have 10 sensors or 9 sensors, we stop and then we run it on the big data. But it's not, I think it will be very useful if you have a very good way to evaluate so that we can pick this parameter, hyperparameter in a better way. Yeah.
So a related question to what he just asked. So have you seen how many senses you are inducing when you compare with some lexicographic resource like WordNet or
WordNet, yeah. So WordNet is, in the sense, it has like 20 senses for words like take or things like that. We don't get that. So what is happening is sometimes we do get extra senses for words, and this I think is like you get some noisy context and you create a cluster. But a very easy hack to remove that is if a cluster does not get enough updates, you just throw it away. We did not do that because we do not have a very good way of like evaluating these things. And if you think of this whole objective where we have multiple vectors for a word, and we pick the maximum one, this is like similar to, for those of you familiar, this is similar to max out training in a neural network. And I think because it corresponds to that, if you look at the nearest neighbors of the MSSG model, even when it has extra senses for a word, the nearest neighbors don't look horrible. And I think it's because even though we get new extra senses, the vectors are still correspond to one of those senses. And I think that's very good. And I think it happens because of this max out style training.
Time for more questions, yeah.
I think the interpretation you have multiple word senses. If you would build multiple clusters, multiple word embeddings, and then see how the word is represented according to these different embeddings, doesn't it come down to the same thing in a way?
Sorry, I don't.
Like you could take the same data or split the data and train multiple embeddings for all the words in your vocabulary. And you could prune some of the word embeddings. In the end, you will have multiple word embeddings per word for some of the words. So doesn't that come down to the same thing? That
Sorry, so you split the training data into say 5 parts.
Whatever.
And then learn just a single vector in each of those parts.
Exactly.
Okay, but how do you sort of ensure that a word like plant always occurs in like the biological sense in one spot?
Do you have to, like, if you do it, if you try it many times, you will see, apple will show up at the fruit, will show up at the company, so you will have different representations.
But how do you ensure that a single split only contains exclusively just one sense? Like
You don't, so you try many times and then, you see.
Yeah, so we have not tried that, and one more drawback there is like every word would have k vectors. If you have k splits, every word has k senses, which is again a problem because that's not true. And we get over that using the non-parametric model. Yeah.
We have some more time, yeah.
Hi, so here you have shown that the nearest neighbors make sense, but I just want to know if you have any comment on the interpretability of the dimensions of individual vectors.
Yeah. So when we look at subsets of the whole vector, we're not sure, like we could not interpret anything out of it. But if you project the 300 dimensions or the 50 dimensions to like 2 dimensions using PCA, the nearest neighbors still look good. They're not terrible. But in terms of whether a slice sort of, so for example, for Microsoft, whether a slice is for companies, a slice is for like Microsoft in terms of products, I don't know whether those things happen. And I'll be very surprised if it happens. Yeah.
Maybe one more question. So I have another question. So, so in some ontologies, there is a notion of a sense pool. So basically, fine-grained senses of words being pooled together. So you can imagine certain representation where you have a vector which is shared across multiple senses of words. Have you thought about that?
So like this is like graded word sense or something, right? Like
Well, so for example, in Ontonodes 5, there are sense pools which clusters fine-grained senses together. I don't know whether it's a good or bad thing, but
okay. So for example, just to give an example, we looked at the nearest neighbors for the word plant, and we observed this happening where one sense is about general plants, then there is a sense that is particularly about flowering plants, and there is a sense particularly about power plants, and then there is this whole manufacturing plant. Yeah, that would be something like, now we are actually playing around with this model, trying to apply to a lot of tasks. Yeah, let's see whether something like that happens. Yeah.
okay, let's thank the speaker and all the speakers of this session.